Good afternoon, and thank you for attending my talk. I'm going to be talking today about polysorbates in biopharmaceutical formulations. So just to start off with, a little bit about Croda. We're a specialty chemicals company that was established in 1925, and I'm here representing the healthcare sector for that business. We supply excipients, vaccine adjuvants, and drug delivery systems to customers all around the world. I'm here today to talk about some of our best-selling and most studied excipients, polysorbates. In this talk, I'll cover the reasons behind the complexity of polysorbates, the common routes by which these products are made, and some of the major impurities found in them. This will then lead on to an explanation about the various quality grades that are available, and then I'll talk a little bit about polysorbate degradation, and finally some of the properties of the major components of polysorbates. There are four areas that cause polysorbates to be very variable, and they are all individually linked with one another as they're all sources of variability. The process starts with the dehydration of sorbitol, and although sorbitan is the main desired product, there is still going to be residual sorbitol and isosorbide present. These three sugars are then esterified with vegetable-derived fatty acids, resulting in the formation of mono, di, tri, and tetraesters. The complexity of the fatty acids themselves, which are generally a mixture of at least 3 to 5 major components, adds an additional level of complexity. The final ethoxylation step results in a Gaussian distribution for each species, whether they both be esterified or non-esterified, which again adds a final level of complexity. So you can probably realize polysorbates are inherently complex mixtures of major components, all of which are different or subtly different. Here we see a moldy TOF spectrum of a polysorbate 20 sample. You can see here that there are numerous species present. And if I'd been talking to this audience a decade ago, this may have been a bit of a surprise. However, as we know, this has been a large area of investigation within the biopharmaceutical sector in recent years, and polysorbate heterogeneity is well known. However, the properties and functionalities of various polysorbate species and impurities is far less understood, and we shall discuss that later. Regarding the major species and looking at the moldy spectra on the slide, we can see all the major components residing across the molecular weight range. Each region highlighted on the slide is essentially a Gaussian distribution of polyoxyethylene chain length, apologies, which is an additional aspect of complexity in the polysorbate. It's worth noting that with the exception of the Chinese pharmacopoeia, polysorbate 80, the fatty acid content is essentially a mixture, as mentioned previously. For example, with polysorbate 80, you have a minimum requirement for the European and US monographs of being greater than or equal to 58% of oleic acid. Typically, though, in most products, it's around about 70%. With polysorbate 20, the mixture is more explicitly defined within the monograph specification. And in this case, the maximum lauric acid content level allowed is 60%. And there are ranges set for the other major fatty acids, particularly myristic and palmitic acid. If we actually look at the synthesis route, we have the standard process by which polysorbates are made, and this essentially commences with a simultaneous dehydration of the sugars and then esterification with fatty acids. Then the sorbitine ester is ethoxylated to make the final product, the polysorbate. There is, however, a reverse process in which essentially the sorbitol is dehydrated and then ethoxylated. It is then finally esterified to make the polysorbate, and hence this is referred to as the reverse process. And some manufacturers do use this as their way of making polysorbates. Despite the fact that these products are intrinsically very complex, I mean, this slide just essentially illustrates how consistently it's possible to make these products with the appropriate controls of the process and the raw materials. The values shown here are essentially based on the percentage of peak intensity by HPLC, ELSD, in which each major component has been separated, as I say, by HPLC. And we show here two of the higher grades material that we commonly supply in these typical sets of data. And it just goes to show, as I say, how reproducible we can actually make this product. Talking about impurities, although polysorbates are a heterogeneous mixture, there are some species that could be considered to be impurities. And there are essentially three classes of impurities. Those that are involved or left over from the production cycle are called, essentially added, if you like, for want of a better word, impurities. They are things like residual catalyst, water, and bleach. They're the oxidation products, which are namely peroxides, low molecular weight aldehydes, and organic acids. And then finally, we have unreacted species such as free fatty acids and soaps, which are typically soaps, as I say, from the fatty acids, but with sodium or potassium salts of these. It's worth noting that various grades of polysorbates can be differentiated in terms of the relative levels of these impurities. The standard pharmacopoeial grade is bleached, contains around 3% water, residual catalysts, soaps, free fatty acids, and oxidation products, such as peroxides, aldehydes, and organic acids. The next grade up, or the HP grade, is a purer, unbleached grade, which contains less water, and while it still contains catalyst residues and free fatty acids, it does contain lower levels of oxidative impurities. And furthermore, it's stored under nitrogen in order to keep those oxidative impurity levels down at the required low levels that we expect from this product. The super refined grades are even purer. In this case, the catalyst residues, soaps, and free fatty acids are also effectively removed. This product also has extremely low levels of oxidative impurities, and it is also supplied and stored under nitrogen. It's worth noting we also supply a grade of superrefined polysorbate 80 that's made from pure oleic acid for particular customer needs. These differences in purity levels can impact the performance of polysorbates in various ways, from the stability of APIs, both small and large molecules, through to the stability of the excipients themselves, and ultimately, therefore, the formulation. Polysorbates can undergo chemical degradation by two main pathways. One of them is the hydrolysis of the fatty acid from the polysorbate ester component. The second is autooxidation, which starts with free radicals to start the cascade of degradation. In the next slide, I'm going to show you some examples of degradation that can happen. In this example of an excipient stability study, where we exposed polysorbate 80 to extreme heat and then stored it for 25 degrees C for 3 months and monitored various impurity profiles, we can see that the acid values do rise after heat treatment in the standard grade material, but not with the high purity super refined grade. This is probably due to the presence of high levels of water in the standard grade, leading to hydrolysis, but also to the production of low molecular weight acids such as formic and acetic acid as end products of oxidation. If we look at the second graph, this just further demonstrates the importance of nitrogen blanketing in preventing peroxide formation. And if you look at the two graphs here, and certainly the graph on the right-hand side, and compare the green and the red lines, this just highlights what happens if you store the material, even a high purity material, under air rather than nitrogen. And that's why we recommend that the high purity grades in particular are stored under nitrogen. Enzymatic degradation of polysorbate has become an area of interest as esterases carried over from monoclonal antibody manufacture can cause degradation of the polysorbate. Enzymatic degradation leads to visible fatty acid precipitates with polysorbate 20, and this degradation can lead to polysorbate loss and therefore loss of API stability and formulation stability. So we've done our own in-house studies using model lipases and our own polysorbates. This lipase is known to be preferentially degrading higher esters, but others can target lower esters instead. We've done similar complementary studies in this area too. We have a standard HPLC ELSD method, which is designed to investigate what happens to each portion of the polysorbate components. The LCMS method uses single ion analysis to actually identify free fatty acids. So we've actually used this technique as well. And for these studies, we've actually added lipase at a particular concentration so that we can actually monitor degradation every hour for 24 hours to show the onset and the progress of degradation. In the case of polysorbate 20 in particular, we also did back this up with visual observations so we can make monitor precipitation. And this is performed with 2 different concentrations of lipase over a 6-month time period. So this slide shows a typical chromatogram we obtained by our reverse phase HPLC method using ELSD. And although I should add that the composition of individual species has been assigned using high resolution mass spectrometry. As with other methods, we essentially separate according to the degree of esterification, starting with early non-eluting alkylating species, including free PEG, and ending with higher tetraesters. In this example of polysorbate 20, we see the same distribution of the peaks irrespective of grade of material, including those found with a pure lauric acid variant we developed for our own research purposes. These chromatograms also show that all grades graded similarly over the course of the study, essentially commencing with a loss of higher esters and the corresponding increase in the non-alkylated components. So this graph is an example of a typical lipase-induced hydrolysis of polysorbates. Here we're showing polysorbate 80. And we're showing this graph in particular because the main point of interest is that those produced by the reverse process appear to degrade much faster, in fact, nearly twice the speed, which will certainly have consequences with regards to formulation stability. In a comparable study of polysorbate level and lipase concentration over 3 days, we can see that micelle size of the polysorbate does change and actually increases with polysorbate degradation. This effect is also most marked with the reverse polysorbates, where the micelle increase is approximately double that of the standard process polysorbate 80. Going back to polysorbate 20, we're just showing a graph here showing the liberation of the lauric fatty acids from polysorbate 20, various polysorbate 20 grades. Here we can see that the superrefined grades start with low levels of free fatty acids, as these are removed by the superrefining process. However, once the lipase is added, the fatty acids are liberated, and we can see that the rate is the same for all variants or all grades. But in the case of the superrefined material, it's starting from a much lower point. It's also worth noting, as some of you may have noticed, that this PLA, or the pure lauric acid variant, is going a little faster. But then, if you think about it, that's not surprising since it's made from 100% lauric acid. And so everything liberated is that acid, whereas the others are actually a mixture, and therefore other acids are being liberated. Here we have the observations at 6 months for different polysorbate 20 grades. And as seen in the previous slide, the lipase will cause degradation, but the superrefined grade will reduce the time for the onset of this degradation to being visible. It's worth noting that material that is made prior to superrefining does show precipitation, and the worst precipitation is seen with the standard grades. As this is a visual grading system, there is some variation, as seen in some of the repeats, but generally the take-home message is that the super-refined materials are far superior in terms of eliminating this problem, or at least minimizing it. Let's talk a little bit about polysorbate components. And polysorbates are added to the biopharmaceutical formulations to prevent protein aggregation. In order to determine which part of the polysorbate is responsible for this effect, polysorbate 20 has been separated into components using chromatographic purification techniques. And we did a lot of our work with the pure lauric acid variant of this polysorbate 20 to try and help simplify things. Done a number of in-house testing, looking at things like general surfactant properties, the aggregation of bovine serum albumin and bovine IgG with guanidine or hydrochloride. So we looked at two different proteins. And we looked at the interfacial liquid using bovine serum albumin again at the solid surface clearance effect. Finally, we also looked at interfacial rheology. So first thing we've done is look at 6 main components of this superrefined polysorbate 20 PLA. And we can see differences in both micelle size and in the sort of surface tension for a stock solution. We've also then gone on and measured the critical micelle concentration. And this is determined using aqueous solutions of polysorbate species and using the intensity of the dynamic light scattering system to determine the point where the micellization occurs. So here's just a typical example of the sort of data we've been achieving using this technique. Here we see that the CMCs for the different polysorbate components, with the neat material PLA having the lowest CMC. And this is probably because these are highly mixed micelles and therefore have the ability to make much smaller spherical species. But as you can see from the other components, there is some variability in the CMC size, depending on the components under study. We look at our first protein aggregation study. This is with bovine serum albumin at 0.2% concentration, with or without 0.01% polysorbates. Whether that be the polysorbate itself or the individual species. And these are sort of concentrations you might find in a biopharmaceutical formulation. The aggregation is defined as the moles of guanidine hydrochloride added, which causes a particle size of greater than 200 nanometers for more than 5% of the mass reading. And you can see from these results that component X offered little protection to aggregation, but all others did. Moving on to the next protein, which is bovine IgG. We've done a similar study here. And again, we're seeing here, though, that there is some differences in the way in which these components are actually performing this time around, where components B, A, and C are, again, giving very good protection against aggregation, whereas components C and Y are showing less, and component X showing very little indeed. So again, it's interesting to note that there is variability in the way in which these components can actually impact the or prevent protein aggregation, depending on the type of protein under study. Just as a matter of interest, we've also compared various grades of polysorbate 80 using the same sort of technique with bovine IgG. And in this case, we looked at various grades made by the standard process. So there's the sort of standard compendial grades, super refined, and HP grades. And then we also compared their performance against those made by what's called the reverse process. And as we can see from the slide above, shown here, that really the reverse polysorbates do not prevent aggregation. The standard materials did so successfully for all the 4 grades under study. So quite a difference between standard and reverse processed material. Quite a significant difference. Moving on, we did some interfacial studies as well using interfacial rheology. And this is used to actually assess the protein clearing from a solid surface. And we use interfacial rheology to basically using a double wall attachment on a TA instrument's DHR3 rheometer. In this study, what we're using is 10% BSA added to the vessel, and then we're adding surfactant at small concentration increments to the aqueous as an aqueous solution. Give an overall dose ranging from 0.0005% weight for weight all the way up to 0.02%. these were added at 3 minutes, and then we then monitor the live changes to the surface elasticity, which we then monitor for a further 2 hours. So as you can see from this graph, polysorbate 20 is very, very good at clearing the interface almost immediately upon adding. It reduces the elasticity to that of water, even at dosage rates at the lowest concentration we studied, which was 0.0005%. We actually also show deionized water just for comparison purposes. But essentially, over the range of concentrations we're using this particular polysorbate, it's very, very effective over the range of concentrations. Polysorbate 80 is slightly slower to clearing the interface than polysorbate 20, but once cleared, it retains its clearance for a whole 2 hours under study. And again, maybe some differences in concentration in terms of the effectiveness of different concentrations, but still, nonetheless, a very effective material for actually showing how it can stop protein navigation at the surface. So just as a summary, polysorbates can be made by standard or reverse processes, and they are complex mixtures of multiple components. We've actually done some investigations looking at the performance of these components in terms of their surfactant properties. I've also talked a little bit about polysorbates. Now they are prone to chemical degradation over time due to impurities present in some of the standard compendial grades. It's worth noting that superrefined polysorbates are more resistant to degradation to their lower impurity profile, and that we've also backed this up with some enzymatic degradation of polysorbates as seen with a model lipase study, looking at standard and reverse processed polysorbates responding differently to the different types of lipases used. I'd like to acknowledge my colleagues and their support in developing this presentation and generating the data. I'd like to mention them from Croda Inc. at Atlas Point in Delaware, Maria Broilo, Brian Maliz, and Kate McAvoy. And then their team over in Croda Europe. This is James Humphrey, Christian Wells, William Small, and Daniel Yates. If you have further questions, please feel free to contact me. My name is Stephen Rumbelow. I'm the Life Sciences Research Fellow with Croda, and my email is shown on the slide. There's Srijit Menon, who's the Research and Technology Manager. And this, again, his email is given as on the slide. And then there's Joseph Matt, who's our Sales Manager for Croda Inc. And furthermore, there's a general inquiries contact email address, which again is available on this slide. So feel free to contact any of us through any of these channels. And with that, I'd like to thank you for attending this talk, and now I'm open for any questions. Thank you.